Hello everyone. Beginning with chapter 6, we'll talk about dynamics. So we're going to talk about the concept of forces and then the application of Newton's laws to various problems. And in this part 1 of the video, we'll talk about forces. So first, what is a force? Force is an interaction between two objects. So force can only exist between two objects. Whenever there's a force, you can always identify two objects connected to it. Okay, so let's look at some examples. The first example that I'm going to talk about is normal force. So what's a normal force? So now let's look at this example. Let's say there's a table. So I use this horizontal line to represent the table. And there's a box sitting on the table. Then there's a force between them. The reason that this box can stay still on the table without falling down, because we know there's gravity. Right? Anything if there's no support will drop down. Now the reason this box is not dropping down, the reason for that is because the contact surface between the box and the table, there's a force pointing upward acting on the box, and this force is called normal force, and the symbol we use to represent the normal force is N. And N exists between the two objects here on the surface, and the reason we have this normal force is because of the microscopic mechanism for that is because of the molecular bond. So let's say if you look at in this surface area in detail, if you zoom in, then we'll see that the surface here consists of various chemical bonds. Okay, so here is just a simplified picture of the structure. In reality, it can be more complicated. Okay, so now let's say just right next to the surface, there are these molecular bonds, and when the object is put here, these chemical bonds will be compressed. So become shorter. And that's a reaction of that. That's because we can model this like a spring. So compress the mini springs. And the spring will apply this force between the two objects on such a surface. So that's why we got this normal force. Okay, so from microscopic point of view, it's because of the compression of the chemical bonds. Okay. All right, so now we know that the normal force can only exist when there's a compression. So we need a contact. Need a contact between two objects. Okay, so let me give you one situation where this contact disappears, and therefore there's no normal force between the two objects. So now let's say I add a force here. Let's say I want to pull it up pull the box up with a pulling force pointing upward. Okay, now we know there's still gravity pulling it down. So I'm going to just draw it, and then we'll explain this later. That's the gravity mg. M is the mass of the box. And when this F increases, so as the pulling force increases, okay, since the box still stationary, still at rest, so the pulling force plus normal force equals gravity. So don't worry about this equation. We'll talk about how to write down such an equation according to Newton's laws. But right now, you can kind of like imagine that they need to be balanced, right? So the upward force need to be equal to the downward force, and then that's the reason this box is at rest. Okay, so now if F increases, gravity is a constant. So if F increases, then the normal force has to go down. Okay, and the minimum value of this normal force, of course, is 0 Newton. Right? Newton again is the unit for forces, and then we talk about Newton's law, and then that's the reason we get this unit named after Newton. And that's the minimum value. So that is the case when there's no compression on the surface. And then there's no deformation of the chemical bonds that we talked about earlier. Therefore, there's no reaction from the mini springs. And that's why there's no normal force. Okay, and that is the situation or the point we call losing contact. And you can imagine that if I increase this force further, let's say it's greater than gravity, then the box will leave the surface, leaves the table surface. Now you see there's no contact at all, right? Losing contact. All right, so that's the concept of normal force. And normal force is not limited to the horizontal surface. It can even be a vertical surface. Okay, so now let's look at this example. Let's say there's again an object, maybe a small box, that you can push it against a wall. So there's a pushing force F acting on the box and then push it against the wall. So now the gravity is still there. So you can still draw this gravity mg pointing vertically down. But the gravity now is not the reason for the compression of the chemical bonds on the surface. Now it's the pushing force. Okay, so F now is the reason. For compression. And that F is the reason that we have the normal force. Okay, so that will introduce normal force N. Okay, so normal force will be the reaction of the spring will be this way. So that's why I can draw normal force to the left. Okay, so the wall's reaction to the pushing force F is to push the box away from the wall. Okay, so now let's talk about another type of force called tension force. Now from the name and also from everyday language, we know the tension force exists in a string or in a rope. Okay, so let me draw a picture of a string or a rope. Okay, so here's a rope. So how can we have this tension force? So usually you will see this situation. Let's say there's an object, and then there's a string or rope tied to it, and then you will generate a tension force in the string, and then that tension force will act on the box by pulling it up. Okay, and also, by the way, T is the symbol for tension force. Now, how can we get this tension force? What's the mechanism for that? It's very similar to the normal force situation, where we have chemical bonds inside a rope or inside the string, and when we pull the two ends, so let's say we apply some pulling force, pulling the two ends of the string or rope, will introduce a stretch. So let's look at the chemical bonds. So these chemical bonds, they're stretched. And these chemical bonds is like, again, mini springs. Okay, so when we stretch a spring, then that spring will react to that by applying a force in the opposite direction. So the chemical bonds or the mini springs, they will try to restore their original length, and that's why you will generate a tension force against the pulling force. Okay, in the opposite direction. So now let's look at this picture. So if you hang an object with the string here, then the mass of the box will introduce this gravity pulling downward, and that is like the pulling force that we have here, and the reaction of that pulling force, which is gravity in this case, is this tension force acting on the box. Okay, so box is trying to pull down the string, and then the string will pull it up by this tension force. So that's the mechanism. And in order to have this tension force, just like in the normal force case, we need to have a contact surface, right? We need to have compression. So in this case here, we need the string to be taut. In another word, you can say you need to pull the string tight. Tight or taut string or rope is the condition for generating the tension force. Okay, now let's talk about the third type of common force, which is the friction force. And there are two kinds of friction forces. The first one is called a static friction. And the second one is called a kinetic friction. So what's the mechanism for the static friction? The mechanism is not actually very clear. However, people have thought about this, and then it's again due to the contact surface here, the chemical bonds. So between the two surfaces, there are chemical bonds forming the instant that you put these two surfaces in contact with each other. So that's these chemical bonds forming across the two surfaces. And then when we try to, let's say, push the top object to the right side, then we're trying to break these chemical bonds. And that's when this spring reacts. They will pull the top object backward with this static friction. Okay, suppose this object here is still at rest. And that's the mechanism for generating this static friction. Okay, so static friction should balance the pushing force that we applied in the horizontal direction. So if I draw the static friction, it should be backside. Okay, so the static friction symbol is Fs. And actually, in the future, when we talk about this kind of free body diagram, we usually draw F to the right side. Okay, so right now I'm just trying to picture this kind of pushing force for you, but in the future, we're going to draw pictures like this, which is called a free body diagram. So the F should point to the right side, on the right side of the object. The object now is a single dot. And Fs is to the left. Okay. All right, so now what happens if I increase this pushing force further? Then the static friction also increases. Okay, so that's the property of the static friction. When I write down the equation here, the static friction is equal to the pushing force in magnitude, but they're in opposite directions. Okay, since forces are vectors. All right. So if F increases, then Fs also increases. Okay, but we also know from experience that if F is large enough, then this object will start moving in this direction, start accelerating. So that means that there's a maximum value called Fs max, maximum static friction. That's a maximum value of the static friction. Once F exceeds that, if F is greater than or equal to Fs max, then the object starts to move. Or starts to accelerate to the right side along the direction of the pushing force. All right, so now once the object starts moving, then we're talking about the kinetic friction. So again, here's the surface, and there's an object sitting on the surface, and there's a actually, you don't actually need a pushing force. If the object is already moving on the surface, then we already have the kinetic friction. So if the object has a relative velocity with respect to the surface, then the surface will apply a kinetic friction to oppose that. Okay, so here's the direction of the kinetic friction, Fk. It's pointing backward to oppose these objects moving. Okay, so let's write down here, Fk is opposite to the relative velocity direction. Okay, now in this case, relative to the surface, the velocity is to the right side. So the kinetic friction is opposing that. It's opposite. So it's to the left side. Now, of course, the friction force is also interaction between two objects, right? So in this case, it's this moving object and the surface. So there must also be a force, right, acting on the surface as a reaction. So again, we'll talk about this like in Newton's third law. But right now, I just want to make the point that the relative velocity direction is opposite to the friction force direction. So if we consider the surface here, then the surface is moving to the left side relative to the object here. So the friction force acting on the surface will oppose this this velocity. So that's why the reaction is this way. So that's the Fk prime, which is acting on the surface. Okay, so now you can see the Fk prime, its direction is again opposite to the relative velocity direction, which is V prime here when we're talking about surface. But when we talk about the object here, when we talk about Fk acting on the object, then we just need to talk about the velocity of the object relative to the surface. Okay, so one more thing I want to go back to the static friction is how to determine the static friction's direction. So Fs, let me write down this first. So Fs is opposite to the moving tendency. Moving tendency direction. So let's see, what's the meaning of moving tendency? So you can imagine that if there's no static friction, if there's no Fs here, then what is the direction of motion for this object? Clearly, if there's a pushing force to the right side, then the object is going to move to the right side. Okay, so in this case, the tendency is moving to the right. It's moving to the right. So that's why the static friction is to the left. It's to the left. Okay, so now let's talk about like how to calculate the static friction and also the kinetic friction. We already mentioned that using the object staying at rest to calculate the static friction. So static friction is equal to F, right? Equal to the pushing force that we have here. So that's one way of calculating Fs. We need this equilibrium condition, and we need this external force F, the other force F. So we need F to determine Fs. Okay. But what happens if the Fs reaches the maximum value? Now, in that case, we have another way of doing the calculation. Turns out that Fs max is given by a constant called mu s times the normal force. So the maximum static friction is related to the normal force. Okay, so let me draw the normal force. In this case, it's from such a surface here, and then the normal force is upward. So I can draw an upward force, normal force. But of course, there's gravity in the vertical direction, right? So the Fs max is related to mu s called the static friction coefficient. Multiplying the normal force. And normal force in this case, the horizontal surface case, is so in this example here, normal force equals gravity. Okay, so that's why I can do the calculation further. So the Fs max will be mu s mg. But I want to make this clear that Fs max is not always mu s mg. So it depends on how you set up the problem, how the normal force is related to the gravity. Sometimes it's not even related to the gravity. So in our previous example, when there's a normal force introduced by this pushing force, then normal force equals F, right? Not mg, equals F. Then in that case, we need to plug in this F to do the calculation of the static friction. Okay, so again, it's not always mg. Now what happens here, Fk? How do I do calculation of the Fk? Now Fk, unlike the static friction has a range between 0 and Fs max. Okay, now Fk has a fixed value, which is given by mu k times the normal force. So it has a fixed value, and mu k is called kinetic friction coefficient. And like the static friction, they're determined by the surface material. Different materials have different friction coefficients, but it's a fixed value once the two type of objects on the surface are determined. Then there's a fixed value for Fk. So it's a constant, mu k. So it's a constant, and it's again related to the normal force between the two surfaces. Okay, usually this mu k is less than mu s. Okay, and that's the reason when we talk about the static friction and kinetic friction in terms of picture, then usually people draw picture like this. So here is the friction force between the two objects, and then the other axis is the pushing force. Okay, so we're drawing a picture for the situation that we drew earlier. So there's a object being pushed by a pushing force, and then there's an F acting on it. Now before this F reaches the Fs max, then the friction force is static friction force, and it's equal to the pushing force. So that's why we need to draw a 45-degree angle for this curve. And then up to this Fs max. Okay, so here's Fs max. Okay, now this curve here corresponds to Fs. Now after that, the friction force drops down to another value, which is a fixed value that we just talked about, given by mu k times the normal force. And this curve here represent Fk. Okay, and no matter how large the pushing force is, Fk is a fixed value. Okay, so that's the picture to remember, and it should be very useful when you try to solve some problem, especially when it contains a Fs here. Fs is more complicated than Fk. Okay, now gravity is the other common force that we need to talk about. So what's gravity? Gravity is because of the universal attraction between two objects, and in this case here is between the Earth. We draw a sphere here to represent our Earth. and another object. Let's say this object here. Let's say it's a box, okay? But now it's in the air, right? So we don't need the contact between box and the earth to generate this gravity. Even if they're separated without contact, there's still gravity acting on a box that we call the mg. Why is that? So the reason for that is because of the gravitational, the universal attraction between any two objects. Then you may say, why don't we consider the attraction between the box and, let's say, another object, let's say another box, a person, a car, etc. The reason is because if both object mass, they're small, if they're both small, by small I mean compared to the earth mass, then that attraction is negligible. You can actually neglect that. Okay, so that's why we only talk about the attraction between the box and the earth. So only talk about this gravity here, and we'll talk about this in the future. But let me write down these universal attractions. Okay, so the universal attraction between two objects are given by capital G m1 m2 over r squared. Okay, so here's the diagram. That's m1, it's m2. These are two masses, and the distance is r. Okay, and capital G here is called the universal gravitational constant. So this law was discovered by Newton, and that explains the solar system, how planets revolve around the sun. Okay, so now let's relate this equation to the gravity that we talked about here, mg. How can I reconcile these two formulas? How are they related? Okay, so now in this case, I want to say m1 is the mass of the earth. Okay, so let's say we have me here to represent the mass of the earth, and m2 is the m that we talk about in this box picture. Okay, m represents the box mass. So now if I do that, then the force formula is given by gme m over distance between the two objects. Right now it's approximately the Earth radius, re squared. Okay, and that equals, now is mg. Okay, since we're talking about their relation, then we need to replace f by mg. They're the same thing. They're exactly the same thing. So that would mean little g here is given by capital G me over re squared. Okay, so again, that's the mechanism for generating this gravity. And in the future, I'm going to just draw this mg on the Earth's surface to represent the gravity acting on the box. Okay, so now with various forces, then we need to think about vector summations, which is called net force. So the net force, the concept of net force is simply just the vector summation of all forces on an object. Okay, so let's look at one example to see this net force. And let's say there's a box, okay, and it's sitting on a table, let's say, sitting on a horizontal surface. Then there's a gravity acting on it, called mg, and there's a normal force acting on it, we call it N. And if we apply a pushing force on the box to the right side, then there's a pushing force F, and the box stay at rest, so there's a static friction to cancel the F. We call this Fs. Okay, so we get net force. Usually we write down sigma F to represent the net force, or sometimes we say F net to represent the net force. Okay, but in most situations I will write down sigma F to represent net force. So the net force is the summation of all forces. So I'm going to write down all the forces here. So I'm going to write down F vector plus Fs vector plus normal force vector plus gravity mg vector. And that is what we call a net force. Now, usually people also decompose the vector into two directions. In the horizontal direction, let's say we call it the x-axis. In the vertical direction, we call it y-axis. Okay, so now let's talk about decomposition of the net force and also each individual force. So sigma Fx equals. Now in this direction, only F pushing force F and Fs are in this direction. So we just need F in terms of whether it's positive or negative according to the x-axis direction, right? According to its relation with the x-axis. So in this case, F is in the same direction as x-axis. So that's why it's a positive F. Okay, so now this symbol F here only represents the magnitude, and its direction is represented by this positive sign. Now Fs, the static friction is to the left side, to the negative x-axis. So we should add a negative sign. And then there's a Fs. Okay. Now in the y direction, we do the same thing. The normal force is positive. So we write on positive normal force. Gravity is downward, so it's negative. Negative mg. So these are the components of the net force. And in practice, when we do calculations, we're going to use this form. We're going to use this component form. So that's the net force. And then you also see the importance of doing decomposition, right? So then when we talk about Newton's laws, we're going to use this component form. Okay, so in x direction, can we apply Newton's second law? And in y direction, can we apply the equilibrium condition from Newton's laws? Okay, so that's the part one of the lecture video about Newton's laws, and it's a preparation for talking about Newton's laws. We introduced the concept of various forces, and then next time we're going to apply them to talk about Newton's laws. Okay, that's all. Thanks for watching. Hello everyone. In this video, I will talk about the non-uniform circular motion in two dimensions. Now first, let's review what constitutes a non-uniform circular motion. Now in the RTZ coordinate system that we discussed in the previous video, let's say here's the circular motion center, and then the radial direction points toward the center. That's the tangential direction, and then there's also this z-hat direction perpendicular to the 2D plane. And we said that we should have the following. Along the radial direction, there's some net force sigma Fr equals MAR, which is given by mv squared over r. Okay, so let's say radius is r here. And along the tangential direction, the net force now should not be zero. It should be something that give rise to the AT. Okay, so equals MAT, and the non-uniform circular motion condition is AT is non-zero. Okay, so we should have some net force along this tangential. Now along the z-hat direction, we should still have a zero here. So there may be some force along this direction to balance each other. And that is the conditions or equations for the non-uniform circular motion. Now, under such a motion, the speed, of course, is not a constant anymore. The speed of the object will change throughout the circle. And that is actually implied by AT non-zero. Okay. All right, so let's look at one concrete example of this non-uniform circular motion. And I'm going to use this vertical circle. Okay, so here the circular path is along this vertical direction, and the radius of the circle is r. And then there's an object, suppose, for example, it's let's say a small block, okay, sliding up. And the surface here is smooth. Meaning that there's no friction to consider. All right, so now let's draw the free body diagram. The surface of the circular track should apply a normal force along this radial direction, and gravity should be in the vertical direction. And since the surface is smooth, so there's no static friction or kinetic friction. And that's it. That's the free body diagram. Okay, so let's write down the let's build the RTZ coordinate system, and then write down the three equations. R direction is along this radial, along the normal direction. Tangential direction is this way, tangent to the circular track. And then the z-hat direction will be in the horizontal direction. So I cannot draw it because right now it's vertical to the screen, right? So I can say z-hat is perpendicular to the screen. And in fact, we don't need to worry about this direction because both normal force and the gravity are inside the plane, so they have no component of their forces along this direction, along the direction perpendicular to the screen. Okay, so another way of saying that is when I write down that equation along the z-hat direction, there's nothing there. Okay. All right. So now along the along the R hat, along the radial direction, the net force equals the normal force is already along that direction. So let's write down normal force first. Now the gravity here, okay, has some angle with that direction, and I'm going to use this angle here. So let me first extend the radial direction, okay, and this angle, I want to call it theta angle, is the same as this angle theta. Okay, so now we need to consider like how to describe, how to introduce this angle theta. So now let's say when the object, when the block is here, the angle is theta equals 0. So that's likely angular displacement is 0. Equals 0 at this instant, and then later on at instant t, so that's t equals 0 second, we have theta equals 0, and then at instant t, we have theta angle, and that's this angle here. Okay, all right. So now with that, when I look at the gravity's component along this radial direction, it will be mg cosine. Okay, that's the cosine component of mg. And it's negative because it's opposite to the r hat. And that equals mar equals m v squared over r. That we want to calculate later on. Okay, now along the t hat, the net force equals, okay, so now we need the mg sine component, and that is negative. Okay, because the t hat direction is pointing along the increasing angle direction, right? Theta increases along this direction, and that is defined as positive direction, and then the gravity is pulling it down, so it's in the decreasing theta direction, so that's why it's negative. And that equals mat. All right, and so how to these are the two equations we have, and then now the question is how to solve at least the velocity information. What is the velocity? In terms of the velocity, we can say if I can find v equals vt, then that's good. But it'll be hard here for this problem. So we're going to just solve for v equals v as function of theta. So let's say we identify the angle theta for the block, and then if we plug in that theta, then we know its speed, and then that's also good. Okay, so let's try to find this expression. Now to do that, I want to do something here. I want to rewrite at as dv dt. Okay, so that's our definition of the tangential acceleration. It will change the magnitude of the speed of the velocity, sorry, and so that's why it's dv dt here. Now with that, I can I can do some integral here. So I want to integrate out the v, and then I want to integrate out this time or the angle. Now time would be difficult, so let's try to integrate out the theta here, the angle here. So what we have here is dv dt, and let me rewrite this as dv dv d theta and then d theta dt. Okay. Now the theta here, if I move it to the left side, then I can do the integral of angle theta. However, I introduce this d theta dt, so let's think about this first. D theta dt is omega, right? It's angular speed. But we also know that there's a linear speed and angular speed relation, omega equals v over r. Okay, so now if I apply that, I can change the variable omega to the linear speed v here, so that I can do the integral. Okay, so now I can let's cancel the mass first, and then I want to move the d theta to the left side together with the r here, and that's d theta, and the right side is v dv. Okay, now I can put an integral sign on both sides, and we need to certify that the correspondence is correct. So for example, at t equals 0 second, we can say the speed here is 0. Okay, so I'm going to start from 0 here. Oh, sorry, not 0. Some initial speed cannot be 0 because the block need to slide up. And at this instant, we have v here. Okay. Now for the angle integral, right, at t equals 0 second, the angle is 0 radian. And then right now it's at theta angle. So that's the integration bounds. Okay. Now let's see. The sine integral becomes cosine, right? Becomes cosine. But there's a negative sign, so we need to absorb that. So it's gr cosine theta. Theta goes from 0 to theta equals 1/2 v squared. So let's plug in the lower and upper bounds and then see what we get. So we have gr cosine theta minus 1 equals 1/2 v squared minus v naught squared. And if I rearrange these terms, I will get v squared equals v naught squared. So you need to move the v naught squared to the left side, so it becomes positive. And then we already multiply 2 on the left side, so plus 2gr cosine theta minus 1. Okay, so a bit of discussion here. So at any angle theta, this cosine theta becomes positive, right? Becomes positive, and it's less than 1. So this subtraction here, cosine theta minus 1, is negative. So you get a value of v less than v naught squared, right? So at any instant, it's less than v naught. So that's reasonable because the when the block slides up, it slows down. Okay. Now in the future, we'll also see that this equation is the same as the mechanical energy conservation. If we apply that, we'll get exactly the same equation. Okay. All right. So that's the one example of the non-uniform circular motion. And then we can actually talk about in detail the object's motion here. And right now it's like an arbitrary position. Now let's focus on some special positions. So again, here's the vertical track. And what are the special positions? So I'm going to talk about the bottom, the top, okay? These two positions. And we're going to study the requirement for the block to reach the top point. Okay, so that's the top, bottom. And then we also talk about at a position say here, the block falls off. Okay, so let's call this falling off position. Let's try to find this angle. So let's say the horizontal direction is this dashed line. Now what's this angle here? When the object, the block falls off. Okay, so let's talk about these three special positions, and then we'll be done with the non-uniform circular motion. Now at the top, first we need to draw the free body diagram. So I'm going to draw it here. So the normal force, the contact surface between the block and the track is above the block. So the normal force is going to push down the block. The gravity is already in this direction. Okay, now this direction is also the radial direction. Okay, and then there's nothing in the t hat tangential direction or the z hat direction, so we don't need to add to draw those directions. Now let's write down the Newton's second law along the radial direction here. So we have normal force plus gravity equals MAR. Let's also replace AR by V squared over R, so that's radius R. Okay, and then that's it. And then we want to find a special speed or the smallest speed, V minimum. What is this V minimum? So that V minimum, so that the block stays. The block can reach the top position. All right, so under that condition, we have normal force equals 0 at V minimum. Okay, so meaning that there's no pressure between the block and the track. So that's the signal for normal force being 0 here. Okay, so now with that, I get mg equals V minimum square over R. So V minimum equals square root of GR. Okay, so now figure out the minimum speed we need for the block at the top, so that it can reach the top without falling off. Now the bottom. Again, first the free body diagram. The normal force is upward now. Gravity is downward. And the radial direction is around the normal force. So that's why when I write down Newton's second law, I have normal force minus mg equals MAR mv squared over R. Okay, so now we don't need to talk about the such as minimum speed or maximum speed, because none of that will make the block falling out the track, right? So we just need to, for here, we just need to calculate normal force. So equals mg plus v squared over R. Okay, so now we can see, because v squared over R is always positive, so this term is always greater than mg. So when the block goes past the bottom of the loop, the normal force is greater than gravity. So that's the gaining weight. One example of this experience would be, let's say there's a car going over the bottom of a valley, let's say. Then the passenger inside the car will feel gaining weight in this process. Okay. All right, so let's talk about the falling off position. Falling off angle. How can I find this angle? Okay, so again, we need to draw the free body diagram. Remember, free body diagram is always the first step. Okay, so I'm going to draw first the normal force. That's along the radial direction. And gravity is this way. Sorry. And as I drew earlier, that's the radial direction. Okay. And then the angle here, that's the angle we're looking for, right? Now, to translate that into the angle that we need here to do the decomposition, let me first draw the tangential direction. Okay. Now this angle is theta, means this angle is theta. So you can write down the Newton's second law in the radial direction. It's given by normal force, the sine component equals MAR equals MV square over R. During the process of falling off the track, the normal force should be 0, right? So that's the condition that we must have here. Okay, so what we have here is mg now sine theta equals m v square over r. So that's the falling off speed. Square root of gr sine theta. Okay. Okay, so that's the falling off position theta, its relation with the speed at this falling off position. So now notice that the speed is not 0, right? It's not 0, so it's something finite. Now in the future, when we talk about this falling off position, again, using the energy conservation, then we can exactly calculate this angle. Okay. All right. So that'll be all for this video. Thanks for watching.